Hello everyone, this is our process control lab in which we are going to perform some experiments related to process control using MATLAB Simulink tools. So in this video we are going to perform the modeling of a first order system using Simulink and compare the parameter wise errors. That means few parameters which parameters belongs to a process, that is dead time, time constant and process gain. Likewise few parameters are there which belongs to a process. So these parameters we need to determine from a process itself. So we will model a first order system first and then check the parameters whatever we are determining from the process and whatever parameter values the process is having by itself, the comparison of these two, and to determine the parameter wise errors. So first of all we will see what are the basic parameters of a process and what is meant by a first order system. Basically a first order system is defined by the total number of poles, or we can also say that the order of the differential equation. That means whatever the transfer function we are having, the order of that system is denoted by the number of poles the process is having, or the transfer function is having how many poles, and we can also say that the order of that transfer function, that means the power of s, it determines the order of the differential equation, right? So order of the differential equation also denotes the order of the system, whether it is having 1, then it will be first order system. If it is 2, it will be second order system, likewise. So we'll see one by one. So basically the basic parameters of a process are dead time, time constant, process gain, ultimate time period. These are the basic parameters of a process. So what is dead time? Let's see first. Dead time is the delay from when a controller output, that means CO is the abbreviation of controller output. Here I have used the controller output signal is issued. Whenever you are issuing a output signal from the controller to the process, until when the measured process variable, that means PV is the abbreviation of process variable, until and unless the process variable first begin to respond. That means whenever you are applying or issuing a signal from the controller to a process, it takes some time. If it taking some time to respond, that time delay is nothing but the dead time. So from this definition we can easily conclude that presence of dead time, that means theta, which is denoted by the symbol theta, this dead time is never a good thing in a control loop. As usual, if we are applying a signal to a process and it taking some time, the more time it takes to respond to that signal, a delay will occur. This delay is nothing but dead time. So dead time is never a good thing for a process. So the formula for theta or dead time is equal to pi minus tan inverse under root kp square k square. Kp square means proportional gain of a controller. K square means k is the process gain, minus under root kp square k square minus 1 whole divided by omega c. And how to determine these values, k, omega c, theta, tau, I'll show further. So next is time constant, that is tau. time constant means it describes the speed of the process variable to respond, right? Or else we can define it like it represents the time needed for a process variable to reach 63.2% of its final value. So, the final value of the process variable, at what value it is going to settle down, the 63.2% of that final value, what time it is taking to reach that 63.2% of that final value, is nothing but the time constant, which is denoted by tau. So the formulas of tau, everyone can note down from here. It will be easier for the further calculations while determining these values. Tau is equal to root over kp square k square minus 1 divided by omega c. This is the formula for tau. So from this diagram here we can see that time constant is this one. It starts responding and the final value is this one. 63.2% of this final value, whatever it is, the time taking to reach from this point to 63.2% of its final value, this time is nothing but tau. And td or theta, the dead time is denoted by theta, or somewhere you will find it like td also. So after the controller signal we have issued, the time taken by the process to respond, that means you can see this is the controller output, right? The controller output begins here, but the process starts responding from here. So this portion td, it is nothing but the dead time, right? So these are the basic idea of dead time and time constant. So now what is process gain, right? Process gain is defined as how far the measured process variable moves to a change in controller output. The process gain is the basis of calculating the controller gain. Process gain, ultimate time period, these are the few parameters which will be required to determine the or model the first order system, right? So ultimate gain, Ku, it is the amount of controller gain resulting in self-sustaining oscillations. That means here we can see this is the oscillation. So initially we need to give we need to increase the process gain slowly, and at what value of process gain we are getting such type of oscillations which is having a uniform amplitude. That means we can say like a sinusoidal wave, right? So having equal and uniform amplitude, this type of oscillations, at what gain value we are getting this type of oscillations, that value is nothing but the ultimate gain, right? Ultimate gain. And ultimate time period, we can say ultimate time period is nothing but for one full cycle what time it is requiring. Suppose you can measure from this point to this, or else you can take it from peak to peak value also, as the output is having equal amplitude. So whatever point you are taking initially, the same point you have to take as the T2 value. That means if you are taking this peak to peak, this will be T1, this will be T2. So T2 minus T1, whatever you are getting, it is nothing but the ultimate time period, right? So likewise you can determine the ultimate time period, right? And how to determine the gain of a process? So gain calculation we can see from here. This one is the controller output, right? So controller output began from 50 to 60. That means the initial value or the input whatever is giving to the process, the controller output, which is nothing but the process input we are giving to the input of a process. So this is the controller output. So this minus this, that means initial final minus initial. I final, which is 60, I initial. This is an example, just an example. While we'll deal with a process of first order process, we'll show you how to calculate. This is I initial is 60 minus 50. So you can see 60 minus 50. As it is a temperature system, it is denoted as centigrade. And the process starts responding from here. So the initial value was 30 and the final value, that means at what value the process has settled down, it is 45, right? So output of the process, final minus initial, that means 45 minus 30. You can see 45 minus 30 divided by 60 minus 50, that means 15 divided by 10, that means 1.5. 1.5 is our value of K, right? So likewise we can determine the value of K. So now we will go further and see how the modeling of a first order system we can do, and we can how we can determine the various parameters, right? So let's go with the MATLAB. So this is the example of a first order system. You can see transfer function, we have taken a first order like 1.0 into e to the power minus 2s, that means theta is 2 seconds divided by 10s plus 1, that means this one 10 is nothing but our time constant tau, right? So we need to determine this k, theta and tau from this process itself, right? Initially we don't know the values. We have taken a first order system. We need to first determine these values, and then we have to compare whether the parameters whatever were determined from this process, practical process, it is coming nearer to that values or not, or same as it is as the first order system we have taken, right? So here I have already calculated these values, so I am just showing you how to determine these values. To make this Simulink model, we need to call all of these tools, that means this is step. From here you can also get from source, sinks, continuous, discrete. This from these blocks you will get the this blocks you will get the basic building Simulink blocks which will require, or else you can directly type it from here. Step, if you type it here you will get the step signal directly, right? You can see that step. You can just click here and drag and drop here, you will get the step. Similarly, it is a sum block, just type sum, you will get the sum block, just drag and drop here. Here it is plus minus. Initially it would have maybe plus for positive feedback or negative feedback, whatever you require. You can just double click on it and change, as I have shown in the previous video also. Then PID controller, so you can directly type PID, you will get the PID controller block here. Just drag and drop. Transfer function also here, transfer function. This is delay, transport delay, this is integrator block, just type integrator. This is display block, you can see whenever you will click in each block, the name it will appear underneath this, right? So just write display, you will get this is marks, this is scope, and just connect this block likewise. That means the process, output of that process is going to scope, and I have taken marks because I need to plot the input signal as well, right? And as I have said, to calculate K, I need to check the input and output value at T1 and T2 itself. So initially I will not connect this part, right, and this part. Okay, so now we will see and we will find out the values of KU and TU, right? So initially we need to increase slowly the value of proportional gain. Just double click on it, it will appear. So I have started increasing this value slowly and was observing at what value I get the sustained oscillation. So by increasing so on, I have got at 8.508. that means at 8.508 Kp value. Kp means in integral and derivative. For PID controller, integral and derivative part will be 0, keep in mind. So I have taken 8.508, not taken, I found that 8.508 Kp value the uniform oscillation or sustained oscillation, right? So you can see here the runtime is here only 10 seconds. Just increase the runtime first, suppose 100. Just see, it is having uniform oscillation or sustained oscillation. So we can conclude from here that Kp is equal to 8.508. we are getting the sustained oscillation. That means our ultimate gain is nothing but 8.508, and from here we need to calculate the ultimate time period, right? So it will be difficult from here to calculate. Just reduce the time runtime, so let's take it as 10. For complete cycle we need to take as suppose 20. we are taking 10 seconds. It is not showing the complete full cycle. Yes, at 20 it is showing the complete cycle, right? So T1 and T2, here I have already calculated. T1 3.250 and 10.697. wherever you want you can take, right? So from peak to peak you can also take, from this point to this point you can also take, as it is an uniform oscillation. So here you can see (3.250), right? (3.250) T1 I have taken, right? And here the final one is 10.697, right? 10.697, up to 3 decimal points I have taken only. So T1, T2 I have also found. So just subtract T1 from T2, you will get the value of ultimate time period, which is nothing but 10 minus 697 minus 10.697 minus 3.250 seconds. You will get the ultimate time period as 7.447 seconds. So TU I have found, KU I have found. Now we need to calculate the other parameters, that means tau, theta and k, right? So for k, one formula I have shown, that means at input of the process and at output of the process, I need to observe the area, right? Here T1 is 3.250, just put it as 3.250. I've got input as 22.22. Just note it down. Input is 22.22 and output is 0.6378, right? And T2 is 10.697. Just make it 10.697, run it. Input area is 28.93 and output is 7.297. So now put it in the formula as I have shown. That means output final minus output initial. That means output at T2 minus output at T1 divided by input at T2 minus input at T1. In this formula you just put these values and you will get the value of k, and from the value of k, ku and tu, you will find out the other parameters like your theta and tau. So the modeling part we have completed here. So now the rest of the part is the calculation part. How to calculate by putting these values whatever we have determined from this Simulink model by observing the outputs. Just put the values on that formula, we will find out the parameters, right? And then we will compare whatever k we are getting, it is close to 1 or 1, exactly 1 or very much close to 1, it will be okay. Then theta, it should be tends to 2, right? And tau, it should be around 1, very much closer to 1. Whatever the value we are getting, are these values or not, we will just check. Whatever error we are getting, we need to conclude that along with the error percentage, right? So this is the main aim. So let's check with the calculation parts, right? So this is the calculation part. You can see as we have got the KU, that means the ultimate gain is 8.508 and our initial and final time for a complete half cycle was these two values, and from these two we have calculated TU like this, and from TU omega you can easily find out as omega is equal to 2 pi by TU, right? So keep in mind whatever calculations we are doing here is in radians. That means we are using these values pi and all this, it should be in radians. Right. So omega c is equal to 2 pi by tu. Whatever we are getting, the value is like 0.843, right? So for k, output final minus output initial divided by input final minus input initial. These are the values. These values we have got from that display in the MATLAB Simulink model, right? So from this formula we can calculate the value of k, which is around 0.992. that means approximately up to 1. Our value for k in the transfer function, whatever first order system we have taken, it was 1 into e raised to minus 2s upon 10s plus 1. That means 1 is our k. So here the value we have got is this. So this is approximately equal to 1, and then we have to find out theta. Theta is pi minus tan inverse, all are in radians. Just before calculating, make sure you are calculating in radians, otherwise the result will come like error, right? So pi minus tan inverse under root kp square k square minus 1, kp square, the kp value whatever we have got, this value into k square, k is our 1, minus 1 divided by omega c. The value we have got is 2.003 seconds. Theta is 2.003. that means dead time. The actual theta was 2, so it is approximately equal to 2 seconds. So it is also verified. And tau under root kp square k square minus 1 upon omega c, right? So from this formula we can calculate tau also, which we have got like 10.02 seconds. The actual tau in our transfer function first order plus dead time model, the actual time constant was 10 seconds, 10s plus 1 in the numerator, so sorry, in the denominator. So tau is 10 seconds, we have got 10.02. so this is also approximately equal to 10, we can say. So all these three parameters, k, theta, tau, we have verified from that first order system. So this is all about how we can model a first order system and how we can determine from that first order system the process parameters, right? So this is all about our this experiments. Thank you.